Fusion and fission are nuclear reactions in which large amounts of energy are released. In the fusion reaction, two hydrogen nuclei are forced together to form a helium nucleus. Explain why a very high temperature is needed for this reaction to happen. Well, you look at the nucleus of an atom, you'll see it contains protons and neutrons. Now, these protons, if you remember, are positively charged, and like charges repel. So nuclei will be inclined to repel each other. So they need to be traveling at very high speeds, and the way to do that is increase their temperature so they have more kinetic energy, so they can overcome that force of repulsion. So high energy needed to overcome the force of repulsion between positively charged nuclei. Remember, that was an explain question, so you had to give a scientific reason. In a fusion reaction, the combined mass of the two small nuclei is greater than the mass of the resulting nucleus. This decrease in mass, m, appears as energy, E, according to the equation, E equals mc squared, that famous Einstein equation. So what we're saying that is the combined mass of the two smaller nuclei when they collide isn't conserved. Mass doesn't seem to be conserved. Rather, some of that mass is converted to energy, so the mass of the nucleus that's produced is lower than you might expect. So can we calculate the decrease in mass using this equation? So we would need to rearrange this to get mass by itself. C is the speed of light, is a constant, which is 300 million meters per second, and the energy released from one fusion reaction is 4.5 times 10 to the minus 12. So we're dealing with standard form again. So we'd rearrange this equation in terms of m. So we'd get c squared underneath. So E divided by c squared will give you mass. So the first thing we do is deal with c squared. 3 times 10 to the 8 times 3 times 10 to the 8. Now when you're doing this, the first thing you do is you multiply the whole numbers, then you deal with the powers, and then you combine your answers. So 3 times 3 is 9. The powers, 10 to the power of 8 times 10 to the power of 8. Unlike division, when you multiply powers, you add these together. So 8 plus 8 is 16. So 10 to the power of 8 times 10 to the power of 8 equals 10 to the power of 16. Now you combine the answers together. So 9 times 10 to the power of 16. So we've worked out the constant of light we've worked out c squared in standard form. Next, we now divide energy by the answer to the bit we've just worked out. So 4.5 times 10 to the minus 12 divided by 9 times 10 to the 16. Once again, deal with this first, then deal with the powers, then combine your answers together. So 4.5 divided by 9 is 0.5. Next, 10 to the power of minus 12 divided by 10 to the 16. Remember, unlike multiplying, when you divide, you subtract this one from this one, the lower one from the upper one. So minus 12 minus 16 is minus 28. So minus 12 minus 16 is minus 28. So now you combine them together, 0.5 times 10 to the minus 28. But if you remember, standard form has to be written between 1 and 9.9, so this isn't correct. So we need to move this here to make it a number between 1 and 9.9, so 5.0. But we just increased this by a power of 10, by a factor of 10, so we need to maintain the value, we need to lower this by a factor of 10. So remember, lowering a negative value means to make it more negative. So this should become 5 times 10 to the minus 29 kilograms. All that for 3 marks. But it's easy, you just need to break it down into the various things, the various components of the question. So rearranging, then working this out, taking into account standard form, substituting, and then making sure you understand how to deal with standard form again. Nuclear fission is used in nuclear reactors in some power stations. In the reactor, a fission chain reaction is maintained and controlled to produce a supply of energy to generate electricity. Figure 14 is a diagram of a nuclear reactor. So you have these movable control rods, you have shields, nuclear fuel here, and a graphite core, which we call and a reactor vessel. So the graphite core is basically a moderator. So some of these are used to maintain and control the chain reaction. So we have to explain how the graphite core, the moderator, and the movable rods are used to maintain and control the chain reaction. So firstly, let's look at what a chain reaction is. You get neutrons being absorbed by uranium nuclei. When they absorb these nuclei, they become unstable and they split, releasing lots of heat, thermal energy, and 2 to 3 more neutrons, which then go and collide with other uranium atoms, which release 3. So you can see this reaction becomes exponential. It becomes very big very quickly. Now, to ensure this reaction is happening, what we have to ensure is these neutrons don't move too quickly. So using a moderator like a graphite core slows them down, and that allows them to be absorbed by the nuclei. We do want them to get absorbed, but obviously we want to be able to slow down the reaction by absorbing these neutrons and stopping collisions, and that's where the movable rods come in. They're lowered to absorb these neutrons. So those are the two ways in which we control the chain reaction. So explain how the graphite core and movable rods are used to maintain and control the chain reaction. So neutrons are released during a chain reaction. That's important to state. Now we deal with the graphite core first. Remember, this is a two-part question. So graphite core and then movable rods. Neutrons need to move slowly so they can be absorbed by uranium-235 nuclei and for fission to occur. The graphite core is a moderator which slows down the neutrons, allowing them to get absorbed. Now the control rods. These can be moved in and out or up and down and control the speed of the reaction by absorbing neutrons, making fewer neutrons available for fission, so less are likely to collide with uranium-235 nuclei. This is actually one of the easier 6-mark questions, and it's triple only.